Welcome back, everybody. This is our first session in NEET previous year questions for chapter Electromagnetic Induction. Before this video, we have made similar videos for the previous chapter for class 12th and class 11th also. And all of those videos are available on our channel's playlist section. We have also started similar series for JEE previous years. So if some of your friends are preparing for JEE or if you want some additional practice, then you can watch those videos also, and those videos are already available in our playlist section. If you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video with question number 1. Let me adjust pen thickness slightly. So here we have a square loop of side 1 meter. Resistance is 1 ohm placed in a magnetic field of 0.5 Tesla. Plane loop is perpendicular to direction of the magnetic plane. The magnetic flux through the loop is. So here loop's plane is perpendicular to direction of the magnetic field. Means suppose if this is our loop, then direction of magnetic field is perpendicular to the plane of the loop. Now to find out the flux, what we need? We need dot product of magnetic field and area. And here this area is in the form of area vector, and area vector is also perpendicular to the plane. So here area vector will be also perpendicular to the plane. So both magnetic field and area vector are parallel to each other, or we can say either parallel or anti-parallel, but most in the cases we take it parallel. So phi will be value of B, that is 0.5, into area, that will be, as side is 1 meter, so it will be 1 into 1, so 1. So flux will be 0.5 Weber. Option B will be the right answer. Let's move to the next one. A big circular coil of 1000 tons and average radius of 10 meter is rotating about a horizontal diameter at 2 radian per second. If the vertical component of the earth magnetic field at this place is this one, electrical resistance of the coil is given, maximum induced current in the coil we have to find out. So we have to find out maximum induced current. For that, what we need, induced EMF, and that should be maximum. So we can say induced EMF, that will be minus d phi by dt, and that will be, here magnetic field is constant and due to rotation area is changing. So suppose this is the axis of the coil about which it is rotating, and this is our coil. So this coil is rotating something like this, means its area vector is also rotating. Area vector which is perpendicular to the plane of the coil is also rotating. So at any time t, the angle uh, between the area vector and the magnetic field will be given by omega times t, where omega is the angular velocity. We know omega into t is equal to theta, so this will be omega t. And as it is rotating, so at any time t, area will be given by a node cos omega t, where a node is the maximum area. So flux will become b a node cos omega t. From that it will be minus d by dt, sorry, minus BA node. Now derivative of cos omega t will be negative sine omega t. So negative sine omega t into omega, and this will be BA node omega sine omega t. Now maximum value of induced EMF will be when this sine omega t is maximum and maximum value of sine is 1. So it will be BA node omega. So that's the maximum value of induced EMF, and from this we can find out maximum value of current, that will be induced EMF divided by resistance. So BA node omega by R. Now substituting all the given values, B is 2 into 10 raised to power minus 5. Area will be, as we have 1000 tons here, so area will be 1000 times area of one coil. So 1000 into pi into radius square, that is 10 into 10, and omega is given to be 2 divided by, this is the resistance, not the radius. Resistance is 12.56. Now this is 10 raised to power 3, 4, 5, 10 raised to power minus 5 get cancelled. We have 4 pi divided by 12.56. We know 5 pi is 3.14, multiply 4 will be 12.56. So both of these are equal. So this will be 1 ampere. Option C will be the right answer here. Let's move to the next one. Magnetic flux linked with the coil given by this equation. Magnetic magnitude of the induced EMF in the coil at the fourth second. So we have to find out magnitude of induced EMF in the fourth second. For that, what we do? First, we will find. First, we write formula for induced EMF. That is, induced EMF is minus d phi by dt, and that will be negative derivative of 5t square plus 3t plus 16, that will give us negative 10t plus 3. And we have to find EMF at the fourth second. So EMF at t is equal to 4 will be minus of 10 into 4 plus 3. So it will be minus 43 volt. We don't have a negative answer here, so we will assume it to be positive. So option B will be the right answer. Now let's move to the next one. A coil of 800 tons and effective area is given, kept perpendicular to magnetic field of this one. When plane of the coil is rotated by 90 degree around any of its coplanar axis in zero point 0.1 second, the induced EMF in the coil. So here plane of the coil is rotated about 90 degree, and initially plane of the coil is perpendicular to the magnetic field. Means we have a two condition here. First the initial and then the final. Let our magnetic field is something like this in the upward direction. So initially our coil look like something like this, that its plane is perpendicular to the magnetic field, and after we rotate it 90 degree, our coil is something like that its plane becomes parallel to the magnetic field. Now in the first case, area vector of the coil will be something like this, and in second case, when you rotate it by 90 degree, area vector will be something like this. So from this we can write that initial EMF, initial flux will be B dot A, and as we know that both are in the same angle, area and magnetic field, so it will be BA. Now final flux will be, as area and magnetic field both are at 90 degree, and we know that at 90 degree flux will be BA cos 90, and BA cos 90 will be 0. So final flux is 0. From this, change in flux is final minus initial, so it will be minus BA, and induced EMF will be minus d phi by dt. That is, d phi is change in flux, so it will be minus of minus BA divided by the time, so it will be BA by time. Now value of B is 5 into 10 raised to power minus 5, area is 5 into 10 raised to power minus 2, time is 1 into 10 raised to power minus 1. So this will be 25 into 10 raised to power minus 7, and we will get here 10 raised to power minus 6, I think. Okay, we forgot one thing. We have 800 tons here. So in area, we will also have to add 800. So multiply 800. Now 25 into 8 will be 200 with two more zeros and 10 raised to power minus 6. So it will be 2 into 10 raised to power minus 2 or 0.02 will be the right answer here. So option C. Let's move to the next one. So, a uniform magnetic field is restricted within a region of a radius small r. The magnetic field changes with time at a rate dB by dt. Loop 1 of radius capital R greater than small r encloses the region R, and the loop 2 of radius R is outside the region of the magnetic field as shown in the figure. The EMF generated is, so we have to find out EMF generated. Now, when we write that induced EMF is minus d phi by dt, and that is minus d by dt of the magnetic field, dot product of magnetic field and area. So it is the magnetic field that is enclosed in this area. Here, suppose we have an area A, our area is something this, then we are only discussing about this magnetic field which is inside this area. If it is outside, then it will not be counted, then magnetic field will be treated as 0. So in the first case, we have magnetic field, and this area is also the area in which there is magnetic field. Like in the first case, uh, suppose this outside this radius of this circle is capital R, and radius of the area up to there is magnetic field present, that is small r. So when we calculate the flux, we will be only taking calculation for the small r part, and that will be inducing EMF in the bigger circle also. So it will be minus d by dt into area, that will be pi small r square into magnetic field that is changing here, so it will be minus pi r square into dB by dt. That will be the induced EMF in the loop 1. Now in case of loop 2, the inside of the loop 2 there is no changing magnetic field, so there is no changing magnetic field, so flux will be 0. So we can say 0 in loop 2, and it looks like that option C and D are same. So either of these can be a right answer. Now let's move to the next one. A thin semicircular conducting ring PQR of radius r is falling with plane vertical in the horizontal magnetic field B as shown in the figure. The potential difference developed across the ring when its speed V is. So when its speed is V, so we have to find out the potential difference developed across the ring. So as from the diagram, we can find out as this cross means that magnetic field is into the page. So here cross means magnetic field is into the page, or we can say B is equal to B node minus of K. Into the page we are taking as a Z direction, and this coil is moving downward as falling downward, so velocity will be in the negative Z direction. So velocity here is V node into minus J. And let me represent the room for you so that you can get a basic idea that how this room is, or how we are taking the dimensions here. So in this room, these are our dimensions. This axis represents magnetic field, Z axis. This axis is X axis and this axis is the Y axis. And our ring is something like this here. Our ring is something like this. Our semicircular ring. So it is moving downward, means it is going down in the y-axis, its velocity in the negative y-axis, and here x and z both are the horizontal direction for the room. If you are standing in a room, then for you there are two horizontal directions and one vertical direction. Then so two horizontal directions are x and z, and in one of them there is magnetic field that is in the negative z direction and coil is moving down. So first of all, as this is a semicircular loop, semicircular, we cannot say it is a loop, it is a semicircular ring. So as it is a ring, means it is not a closed loop. So there will be no flux associated, because flux is associated only when you have an area of a loop, and we assume that this ring is of very we can say very small value of thickness, so it will not have any appreciable area, so there will be no flux associated with the coil. But this coil will act as a moving conductor. This coil will act as a moving conductor in magnetic field. And for moving conductor in magnetic field, we know that induced EMF is given by B dot product L cross V. Means to get the induced value of induced EMF here, we have to first calculate the L cross V, and that L cross V should be in the same direction as of the magnetic field. So here magnetic field is in negative K direction. So it is in negative K direction, and we know the velocity that is in negative Z direction. So the only possible value of length which we can take and we can calculate the induced EMF will be here I. If we have our length in the I direction or in the positive X direction, then I cross J will be negative K and we will get value of induced EMF. So the length which we need to take here is along the X axis, and along the X axis length of this semicircular ring, that will be this, or we can say it is a horizontal projection of this wire, and that length will be equal to twice of the radius. So B as it is, length is 2 of r into velocity, so it will be 2 r b feet. So that will be the value of the induced EMF. Now let's find out that which point will be at a higher potential and which point will be at the lower potential. So as we have P and R points here, and as this is a metal wire, so there will be some electrons, and on those electrons we can find out the force acting on them. We know that force acting on a moving charge particle is given by Q V cross P. As we are discussing here for electrons, so their charge will be negative, so minus E. Their velocity, as whole wire is moving downward, so their velocity is in the negative z direction. We are only discussing regarding direction here. And magnetic field is in the negative k direction, so it will be the negative k direction. So negative negative will be positive, j cross k is I, and with negative sign, so force on electrons will be in the negative x direction. Means all of the electrons will deposit toward point P, and if they deposit towards point P, then on the point R we have a, we can say, positive charge. So point R will be at higher potential, and point P will be at lower potential. So 2R BV with R at higher potential, option D will be the right answer here. So let's move to the next one. Coil of resistance 400 ohm is placed in a magnetic field. If the flux linked with the coil varies with time with this relation, the current in the coil at T is equal to 2 seconds. So current in a coil will be given by induced EMF by resistance, and induced EMF is given by minus d phi by dt. So it will be minus 1 by R. D phi by dt will be 100 of T. So we can substitute values here now. 100 into T, that is 2, and resistance is 400 ohms. So value of current comes out to be negative zero point 0.5 ampere, and that is option A for us. Let's move to the next one. A conducting circular loop is placed in a uniform magnetic field with value this, the plane perpendicular to the loop. The radius of the loop is made to shrink at a constant rate. So here a radius is changing. If radius is changing, means area is variable here. The induced EMF when the radius is 2 centimeter. So till now, whenever we have solved all the questions in the previous, can say up to 7 questions, either our area was changing due to rotation and our area was equal to a node cos omega t in the normal cases, or we got a changing magnetic field. But in this question, our area is changing, but not due to rotation. It is changing due to shrinking of changing of the radius. So normally, induced EMF that we have, that is given by minus of d phi by dt, it is equal to minus d by dt into b into area. Here b is constant, so b will be outside of the derivative. D by dt of area, that is pi r square. Pi is again constant, so it will be minus b pi d by dt of r square, and it will become minus b pi. Derivative of r square is 2r into dr by dt. This is the value of radius at any particular time, and dr by dt is the rate of change of radius. So magnetic field is 25 into 10 raised to power minus 3 into pi, that is as in options we have pi, so we keep it as it is, pi twice of radius, that is 2 centimeter given, 2 into 10 raised to power minus 2, and dr by dt is 1 millimeter per second. 1 millimeter per second means divided by time, and as this is shrinking, means dr by dt is negative here. As radius is decreasing, dr by dt is negative. So negative negative will become positive, and we will have 25, and this is 4, so 100 into pi minus 3 into 2 minus 5 into 3 minus 8. So this we can write pi into 10 raised to power minus 6 or pi microvolts. That will be option B for us. Now let's move to the next one. As a result of change in magnetic flux linked to closed loop as shown in the figure, the EMF V volt is induced in the loop. The work done in taking a charge q coulomb along the loop is, so we have to find out that work done, what needs to be done for taking a charge q coulomb along the loop. So this question can be interpreted in three different ways. Oh, sorry, in two different ways, and let's discuss all two cases. First is when we are discussing regarding normal work done, that initially when there was no induced EMF, so initial potential linked with this loop was zero, and after induced EMF final potential is equal to potential V, and from this we can say work done that is equal to Q times change in potential that we need to transfer, so it will be QV. But all these calculations are applicable when we move a charge from suppose potential Vi to potential V final. Means at the time of movement we have both of the potentials present with us. We have at one location we have initial potential, and one location we have the final potential, and when we are moving charge from one point to lower potential to higher potential, this is the amount of work that needs to be done in the moving charge. Now, in this regard, our answer can be option A. Now coming to the second case. Now as we induced some EMF here, so on this whole wire, we have the same potential. In this whole wire, we have the same potential because this is a connected wire. And as we have the same potential here, or let we can say, uh, assume there is some resistance in the wire. If there is some resistance in the wire, then there will be some positive part of this wire and there will be some negative part of the wire, so that we can represent it like this. In this loop, this is the positive part, and this all other wire is acting as a resistance R. So we can represent this circuit like this, where V is the induced EMF. Now in this case, if we are moving charge from one point at the second point, these 2 points will be at same potential in this case, so work done will be zero. But if we are moving from point A to C or C to A, then work done will be QV. So it is not clear in the statement that in which way we have to move, and at the last it is mentioned that q coulomb at along the loop, once along the loop. So if we move it in a closed loop, in that case work done will be QV. So we go with answer A. Now let's move to the next one. A rectangular coil of 20 tons, area of cross section 25 square centimeter, resistance 100 ohm, magnetic field which is perpendicular to the plane of coil changes at the rate of this. So we have to find the induced current. We know that induced current will be induced EMF by resistance, and induced EMF is minus of d phi by dt, and here magnetic field is variable, so area will be outside, so minus A by R into dB by dt. So here area will be, as we have 20 tons, multiply the area of one ton, that is 25 square centimeters, so 25 times power minus 4 divided by 100, that is resistance, and dB by dt, rate of change of magnetic field, that is 1000. So two zeros cancelled. We have 25 into 20, that is 500, into 10, 5,000 with negative sign 10 raised to power minus 4. So it is negative zero point 0.5. Option C will be the right answer here. So with this, we end this video here. Again, if you find this video useful, helpful, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.